Hi everyone, I'm Abhishek Choudhary and here's my colleague Kunal Bhalla, and we are going to talk about the battery instrumentation of our Android apps. Monitoring battery usage is very essential because high battery drain is one of the key reasons for uninstalls in emerging markets. Also, if your app is draining battery really fast, it will hurt the overall sentiment of the users. A quick overview of what we'll go over today. We are going to go over the difficulties with measuring battery and the common misconceptions around that. Then we are also going to go over how can we instrument battery in production and use a power model to estimate how much battery your app is draining in the wild. Once we have the measurements, we are going to talk about how can you use those measurements to fight regressions, and finally some key points to keep in mind for being a better battery citizen. So what are the difficulties of measuring battery? Imagine getting a battery report like this. Uninstalling your app increases my battery life by 9,000%. What do you do after this? How do you debug this issue? So let's look at what are the existing options I have now. So the first and probably the easiest thing to do is just fire up the Android profiler in Android Studio and view the network and CPU usage as I'm browsing through the different features of the app. The problem with this is it doesn't cover camera and location access, which are one of the key reasons for battery drain. The other tool that you can use is Trepen. This basically shows the real-time current being drawn by the app as you are using the app. It will also show you the current CPU frequency, and you can actually go to different products in your app and see how much is the current being drawn. And if you see somewhere that the current being drawn is higher, you'll probably know that this is a problem. However, the most accurate way to measure the power drained by the app is probably by using a power monitor. This is a device that you can connect your phone to and then measure the current being drawn by the phone. The way it works is you basically take out the battery from the phone, connect the power monitor cables to the device, and then the phone starts drawing power from this device. And you can see how much power the phone is drawing from this device by connecting this device to your laptop, and then you can see the real-time current being drawn. This is an example of me playing with the power monitor. I'm just increasing the brightness I'm just playing around with the phone and increasing and decreasing the brightness or opening the camera, and the current goes up and down. It's not moving somehow. Anyways. Yep, that's the current going up and down as I'm opening and closing the camera or increasing the brightness. However, these tools that I mentioned before, the Android Studio, Trepen, or the power monitor, these require you to play with the app and then monitor the current real time. The tool that will come in most handy for debugging issues in the wild is the battery historian. This is basically a UI to view all the battery logs in the phone. So Android OS actually records everything that is happening in the phone, like CPU network usage of each and every app, how much time the phone was connected to the network, radio, Wi-Fi, everything. And it records it till either the buffer overflows or the phone is charged to 100%. The way to take this report is go to developer settings and click on the take bug report button, and then you get a zip file, and you can feed that zip file to this battery historian tool. Once you feed that file, you get something like this. This shows a timeline of everything that was going on in the phone. It will show you the job scheduler jobs, network connectivity, almost which was the foreground process, how much time you're using each app for, the network CPU usage of every single app, and then you will know what exactly was going on and why your app was taking up more battery. The issue with this is this has to be triggered by going to developer options. So you can't really expect many of your users to do that. Also, this report has privacy-sensitive information, so you can't really expect a lot of these reports to come in from the wild. Only if you or your colleague is having battery drain issues, you can go and take this report and look at, okay, what was draining your phone in the night? So it's not something you can use to instrument battery in the production. So all the previous ways that I mentioned, you have to either play around with the app or you are able to reproduce the issue locally. But if you're not, then these local measurements are not enough. And at our scale, it doesn't work. At our scale, we have an enormous amount of code, like thousands and thousands of lines of code. running on 1 billion devices under various different conditions, being updated daily by several hundred developers, and several hundred experiments being tweaked dynamically. At this scale, how do you figure out why your app is taking up more battery in the wild? Clearly, to fix the battery drain issue, you first need to understand it. And understanding why and how your app is draining battery in production is not trivial. Let's see what we tried. So the first typical approach that we tried was measuring the battery usage, the battery device level, the device level battery when the user starts using your app, and then taking the snapshot of the battery level again when the user exits your app. So when you start using the app, the battery level was 50%. When you background the app, the battery level was 47%. So your app drained 3% battery. However, this didn't work out. The reason is there are some key problems with this metric. First of all, it's very noisy. When your user is using your app in the foreground, there can be other apps running in the background. There can be a location tracker running in the background that's accessing locations via GPS, and that's responsible for the key amount of battery drain and not your app. Also, there might be apps updating in the background. The battery might be degraded, and hence the battery level is going down very fast. It goes down by 5%, but maybe your app is not responsible for the 5% drain. It's just because the battery is bad. The second problem is it's very coarse. The battery level decreases at a granularity of 1%. It's very rare that users typically use your app for like a minute or two. It's very rare that the battery level will drop by 1% during that 1 or 2 minutes of usage of your app. In that case, what will happen is most of your samples will end up becoming 0. But that doesn't mean that during that 1 or 2 minutes, your app used 0 power. Your app was using power, it just wasn't enough to tip it over that 1% mark. Thirdly, it's inaccurate. The battery level exposed by the OS is not very accurate. It only exposes you a monotonically decreasing view of the battery level, whereas in actual, the battery sensors are going up and down based on some ambient conditions like temperature. Also, 1% battery on your phone doesn't really mean 1%. It's usually 3 to 4%. The OS just tries to warn you earlier so that you can charge your device. So given that this approach didn't work, how can we accurately measure our own app's battery drain and not the device? One idea was to ship Power Monitor to all of our users and ask them to measure the power usage and email us the reports. Not everyone agreed to this idea, so Kunal will talk about how we measured our battery drain in production.
So unfortunately, we couldn't use Power Monitors as much as I wanted to. So we tried to do something slightly different. And basically, we took the approach that is taken by most battery setting screens, where you look at the consumption of each different hardware component, and you try to figure out the utilization of that component, and then you map that utilization back to actual battery drain. And that gives you a sense of how much energy was consumed without all the shortcomings Abhishek just covered. Over the next few slides, I'm going to talk you through the different hardware components we measured, how we measure them, and then how we instrument all of these values. Let's start with the most obvious one, CPUs. CPUs are pretty good in mobile phones. They'll try to downscale their power consumption depending on how much work you're throwing at them. As you increase the load applied to your phone, the CPU will increase its frequency and consume much more power accordingly. Generally, the energy consumed by the CPU varies as the cube of the frequency, and you can see that in this curve here. Some phones also have 2 different types of clusters, like ARM's big. LITTLE architecture. So you'll have a smaller set of CPUs that are very cheap to run and will almost always be on and doing all the things that the phone needs to do. And then you'll have some really large and powerful CPUs that are very, very expensive, but will only come into play when you're playing a game or something like that. And you can kind of see these curves from a Samsung S7. The green curves are from the green bars are from a larger cluster, and you can see just how much more expensive that is from the orange one. So being aware of how much CPU frequency you're using is also kind of important. If you're from Linux, you're pretty familiar with this. We just look at CPU time by looking at procfs and grabbing the stat values. You can also use the same approach to measure thread level CPU utilization. For CPU time and state, you can get something at the full phone level, device level. So you get how much time the phone was spending at each different frequency. And then you can kind of say, okay, my phone was at, say, 100 frequency and 200 frequency for half the time, so I'll just distribute my CPU time accordingly. And that kind of maps to energy consumption for you. You'll also see a reference to health stats up there. So that's an API Android added from N+, which is really useful. It gives you all of these statistics for CPU utilization, and it's really good. There are a few shortcomings. One is that it's N+ only, which is kind of a big problem for us. And the other is it might not be there. Sometimes it stops recording data if you're charging for some of the metrics. So if you want a completely comprehensive view of your app, you might still want to instrument it yourself. I'll be mentioning health stats in almost every slide after this, but I won't cover it again because it applies to pretty much every hardware component I talk about. Radios. One of the more interesting things I learned about radios was about tail time. If you've read about battery instrumentation, like how to not be a bad battery app, everyone will tell you to batch your network requests together. And this is kind of the reason. Every time you try to send a network request, the radio goes to a high power state. It'll transfer the data you asked it to transfer. Then it'll stay at that high power state for a few more seconds, just in case there's a new reply or you want to transfer more data. After that, it'll go to a middle power state, wait another few seconds, and again, waiting for anything to happen. And finally, it'll give up and go back to the baseline. What you see here is a sample app we wrote that basically sends small batches of data. And you can see it going to the high power state, then spending all the tail energy, and then finally returning to baseline. If you were to batch these requests up, then you would only spend this tail time once, and that's much cheaper. The actual time the radio spends at each of these states is very network dependent. Like between 3G versus 4G versus 2G, you're talking like 30 seconds to 20 seconds to 4 seconds, and different times for both high and low power state. They're also decided by the mobile network provider themselves. The cell tower tells your phone how long the radio should stay on. So this is pretty interesting, and this kind of explains why you care so much about these values. For Wi-Fi, the tail times tend to be in just milliseconds, so we don't care about that so much for Wi-Fi radio. Measuring this, it's very easy to measure the total bytes transferred. Like Android has a nice traffic stats API. There's a kernel module called quota tag UID, QTag UID, that basically tracks bytes transferred per socket in your Android app. And then you can kind of get a breakdown by Wi-Fi versus radio and other things, and just read that file. And of course, health stats. There was no good way for us to measure the radio time, unfortunately. So for that, we just made a custom state machine that you can just poke. So every time we did a network request, we would say, OK, network request started, the radio is probably on, and then let it time out automatically. So that lets us get some sense of like how long the radio was on and look up batching correctly. Cameras. Cameras are really, really resource intensive. Like opening the camera and running it can kill your phone in around 4 hours or so. The energy consumed by the camera depends on pretty much like as you would expect it to. More resolution means it's more expensive. Higher frames per second means it's much more expensive. And there's a difference in the cost between the front and back camera as well. We've also noticed that as our phones have kept getting better, the camera has been getting much more expensive. A 2012 year class device used to have a much smaller and cheaper camera than something in a new, like 2015 year class device like a Samsung. Measuring these, unfortunately, was again by hand, artisanal. We just had to like wrap every single API call and decide whether the camera was open or not. Before I move on, one thing I'd like to call out, just opening the camera, even if you're not previewing it, does cost power. Quite a few people seem to assume that just opening the camera is free. That's not true. You power on the camera hardware, you start paying for it instantly. Location is this magical hardware component because that's how the OS exposes it to us. Like you don't actually get to interact with the GPS directly. You just say, I want a high accuracy location request, or I want a medium accuracy location request, and something happens. The way we've been modeling it is to treat a high accuracy request as something that switches on the GPS. And that's how we charge the device, charge the app for it. Same way for medium requests, we just say that this is probably a Wi-Fi scan. And for requests with very low accuracy, we just say this is probably free for us. And that's worked out pretty reasonably. Again, we do instrument this by hand, like kind of repetitive, sadly, but it's a bit painful, but you can get all of this information, and it's generally worth tracking carefully. GPU. I'm kind of hoping someone will say that give me an answer right now and stand up and tell me I'm wrong. But we haven't found a consistent way to measure GPU in production right now. Like for each different manufacturer, we've seen like different counters being exposed. Sometimes from the same manufacturer across different phones, they'll have counters at different places, and mapping those counters to energy consumption has been fairly tricky. So for us, measuring GPU in production is kind of a question mark right now, and something we were a bit worried about. Screens. In practice, your screen is probably the thing that consumes the most energy from your phone. Like as you use it every day, and assuming you don't have any bad apps installed, this will be the thing that drains the most energy. But as an app developer, there isn't too much you can do about it. Like you don't want to just go and reduce someone's brightness to 0 because to save a little bit of energy. And so we don't tend to track it as much. One more option you do have, like for OLED screens, if you convert your application to be mostly black, it'll save a bit of energy. But again, these are trade-offs we didn't consider worth making. Taking a step back, this is what the energy consumption per hour by device looks like. These are all numbers pulled from a Galaxy S7. You can see how the energy consumed varies a lot. Like large cores running at 100% are ridiculously expensive and kind of start heating up your phone. Then there's the camera. Opening the screen at max brightness versus min brightness, there's almost a difference of 5 times energy consumption. And right at the other end of the spectrum, CPU idle is almost free. All right. So this was how you can kind of measure all these numbers we talked about. But how do you want to look at them? How do you want to break them down? The first thing we did, or the most useful thing for us, was to break the numbers down by whether the app was actively being used or whether it was in the background. You really, really don't want to consume someone's battery while your app is backgrounded. So we try to push these numbers down to 0 as far as possible, and then look at when the user is actively engaged with Facebook. At that point, it's still reasonable to consume some energy because they're finding value in your app. So the way we collect this is that at every session transition, like if your app is going from foreground to background, we'll snip out how much energy, like how these metrics varied over the past session and upload it at that point of time. There is a small caveat though. Like if you just rely on these session transitions to upload data, there is a chance that you're going to lose data. Like anytime your app crashes or if it's in the background and it dies, you're going to lose that last session. So that foreground session with the dotted line, you might not get data for that. So as an alternative, we also try to log data to disk every so often. So in case the last session couldn't get uploaded normally because your app was killed for some reason or the other, we'll just upload the previous session and make sure that our data is reasonably complete. Another blind spot that you might accidentally have that I'd like to call out is to don't forget any secondary processes. Like if your app is spawning secondary processes because it's complex enough, do make sure that you instrument it separately. Like one common thing you can think of is that you might get CPU time just because it's a child process, but that's not true because Zygote spawns a secondary process from Zygote. So that's not going to be a child process of your main app. Depending on how your thing is, like how your application is implemented, you might be able to have analytics in your secondary process uploading data. If it's lightweight, you might find it more valuable to just save to disk. We tried to do it in a way that didn't make any assumptions about how the life cycle of the secondary process went. So our secondary processes keep saving data at regular intervals and keep adding up values because the secondary process might die and start multiple times in the same session before the primary process gets a chance to read them and upload them to the server. Most importantly, don't drain battery to measure battery. This instrumentation is really pervasive. It's like happening at almost everything your app is doing because you want to measure everything your app is doing. So it's very, very easy to accidentally start draining a lot of additional power just to measure what's happening. Don't set a scheduler job just to wake up your app and upload a metric to the server saying that your app didn't do anything. Wait for the app to actually do work and then use that to piggyback onto it and then upload something to the server. Sample data aggressively. You don't need to collect data for every single user, so we kind of subset it a lot. And if you want to be even nicer, you can also keep rotating that sample so that the same set of users aren't paying the cost for everyone. So you've done all of this, and you end up with something like these 8 graphs with a power metrics dashboard that shows you CPU time, device battery consumption, radio time, all the metrics we just talked about. And we tend to track these at different percentiles. So we can see like P50 is varying, P99 is varying, and quickly catch outliers. This is just a graph from our alpha beta for background usage. So we have like 4 sets of these: alpha, beta, foreground, production background, production foreground, and this is getting slightly nuts. Tracking these across releases and making sure nothing regressed can be fairly painful. It's also very hard to go to a product engineer and say, you're causing a 5% CPU regression, you can't ship this. And they're like, why would I care about causing a 5% CPU regression? Or sometimes you get a question like, if I'm reducing network radio time by 20% but increasing CPU by 5%, is that a good thing to do or is that a bad thing? So we ended up wanting to map this back to some sort of physical value that says that this is the effect on actual battery. And that brings me to modeling battery drain. So to do this, we ended up taking the same approach as the battery settings screen. Every Android device ships with a power profile. This screen is basically powered by that power profile. That describes the cost of each hardware component. It tells you that running the CPU at a certain frequency consumes so much energy, switching on the screen consumes so much energy, using the camera consumes so much energy. This is obviously, there is a lot of approximation involved in this, and this is pretty well defined in the AOSP page, but it gives us a pretty good way to go back from all of these proxy metrics to the energy costs. We also try to sanity check some of these power profiles by spot checking them with the power monitors we talked about earlier. For the most part, they were good. There are some phones that do ship with the default power profiles that AOSP provides. Like AOSP gives you a power profile that has ridiculous values just to point out that, you know, this is what you have to fill in. And then you go into production and then you see a power profile and it's like, nope, they just copied and pasted it into the device. So just be careful when you use these. For our case, we kind of try to just default it to the same valid power profile from the same year class whenever we come across a bad power profile like this. And then we can take all of these proxy metrics we measured with the power profiles we have and then get a nice battery drain number that is much more stable, isn't dependent on like physical conditions, and is much nicer for us to track. Going back to a very familiar slide, with model battery drain, it's no longer noisy because it's not affected by other apps running on the device anymore. It's not affected by physical conditions or ambient light conditions because it's just what you are doing. It's not coarse anymore. You're like measuring CPU at CPU time in milliseconds, camera in milliseconds. So everything is much more accurate and you can actually catch all the small regressions that are happening. It's not trying to smooth over an app's like battery deterioration. It is approximate, but it's no longer inaccurate at the very least. So with all of this, we finally ended up with a model battery drain dashboard that shows us like how the app is performing release over release. And the way we looked at it was the percentage of battery drained per foreground hour used by the user. So that kind of lets us normalize someone's utilization of Facebook and see that background isn't increasing and foreground is constant. Like if foreground energy increases because we're normalizing by foreground time, that lets people ship products that actually make people use Facebook more. If you didn't do that, like anything that makes people use Facebook more would regress this, so we normalize it by the foreground time as well. We also use this for all of our A/B tests now, and now we can say that you're regressing Facebook's battery consumption by 10%, so you can't ship this product, which is kind of what ended up happening with this experiment, which, as you can see, ended up increasing energy by 11%. So now that we have all of this in place, are we in a good enough position to fight regressions? That's what Abhishek is going to talk about.
So now that we have a metric that we can track across releases and for our A/B tests to detect regressions, what happens when these regressions come? Let me walk you through a real regression story. So one day we see this power graph going up. This is basically the same graph that Kunal showed earlier, the power drain per user per foreground hour. On one side, I'm glad that we are now detecting regressions from our graphs instead of user reports. And the first thing that comes to my mind is this has to be caused by either of the 4 hardware components because we modeled this number based on the addition of power consumed by these 4 hardware components. So then I go and look at the graphs for these 4 hardware components. Well, CPU clearly seems to be rising. Network, camera, location, relatively stable. So our app has started taking up more CPU. Now what? Remember, every single line of code is a candidate to this regression. And our app is so huge, you can't just sit down and navigate through all the endless products and see which product has started taking up more power. How do you attribute these regressions to a line of code? So catching regressions was easy. You just need to spot a spike in a graph. Solving them, maybe not so easy. So what we realized was we need more attribution instrumentation. We need to figure out that why we are taking up more CPU, ideally to a line of code. So let's look at what we did. So earlier we were only measuring process level CPU usage. Now we start measuring the thread level CPU usage. So whenever the process level CPU usage goes up, you know which of the threads have started taking up more CPU. Now, if you're lucky, this thread will be accessing one function in the code base, and you know that that function has started taking up more CPU. If you're unlucky, it will turn out to be a shared thread pool that's accessing a ton of code. So it still doesn't point you to the exact problem. So then we came up with another tool called the CPU spin detector. What this basically does is we measure the process and the thread level CPU usage at regular intervals. And if the CPU usage during the last interval is greater than some certain threshold, that means our app was taking up a lot of CPU during that last interval. So then we figured out what was the most expensive thread, the thread that took up the most amount of CPU time in that last interval. We find out that thread, and we take a stack trace of the thread, and we upload it. The way it looks is, this is the life cycle of the app, and the green line is the green graph is the CPU usage of the graph of the app, and you can see the vertical lines are the points where the CPU spin detector is running. The red line shows that the CPU spin detector detected that we have used very high CPU in the last interval. So at that point, we take the stack trace of the thread. Now, if you notice carefully, it's not the point at which the process is taking up the most amount of CPU. So if you look at the stack trace from one device, it won't make much sense because it's not necessarily the point at which the process was taking up the most amount of CPU. But when you start aggregating this data across multiple devices, because this thing is running in like millions of devices. So if you start aggregating this data, you ideally get a stack trace that points you to the root cause. The stack trace aggregation is similar to what you will do for crashes. This has proved like very, very beneficial to us and has helped us solve like multiple regressions in a matter of hours by giving us the exact stack trace to go after. There is one more interesting case of CPU drain, and that is the animation leaks. This is basically an animation is running on the screen, but the user cannot see it. And that causes the OS to redraw the screen again and again, thus wasting CPU. To see this example, on the left-hand side of the screen, if you see, it's a pretty static screen. There is nothing changing on the screen. But the bars moving from the right to the left, they basically show that the CPU is constantly running and the OS is redrawing the screen again and again, even though there is nothing changing on the screen. The bottom graph shows our CPU usage is 35 to 40%. Basically, we are using 35 to 40% CPU for giving out nothing to the user. On the right side, the same thing, animation is fixed, and we are no longer re-rendering the screen again and again, and the CPU usage has gone down to 0. You might think it's very difficult to cause this. It's not really. Let's look at this code. Does anybody see anything fishy with this code? It's the same code that was responsible for the previous slide. Well, if you notice carefully, we are passing the same instance of color drawable to the background, selector, divider, footer, all of them. Each of this component ends up resizing this color drawable, so the OS thinks that the view has been invalidated, and the OS starts re-rendering the screen again and again. The simple fix is to just pass a different instance of color drawable so that the OS knows that its height and width are not changing, so there is nothing to render again. Back to attribution. I talked about CPU. For network, almost every product on the Facebook app uses network. Newsfeed, photos, videos, marketplace are just 4, but there is an endless list. So if the network power starts going up, what we do is we basically instrument based on the call site and product. We know which call site is accessing network, is transmitting and receiving how many bytes, and is keeping the radio awake for how long. So when the overall network part starts going up, we know which product has started taking up more network. And then we can reach out to these product teams and get the issues fixed. Camera is similar, again, used by multiple products in the code base. The instrumentation is very similar to network, where it's based on the call site. We know which product opened the camera for how long, and that helps us attribute the regressions to a particular product team. There is one more thing we do for camera called the camera leak detector. In Android, it's possible to leak the camera. Like you open the camera and you forgot to close it, and the camera will stay alive and keep consuming power. What this does is basically we detect if the camera was opened in the background, and this tool will start shouting. The other thing it does is if the camera was opened in the foreground and then the app was backgrounded without the camera being closed first, this is probably a case of camera leak. And the camera leak detector is useful in the sense like it helps you attribute regressions to a line of code. It will exactly tell you from what line of code the camera was opened and then never closed. Location, again, used by multiple products. The instrumentation is similar to what we did for network and camera. Based on the product, we know which call site is accessing location for how long, how many times, and at what accuracy. And then you can figure out which product to go after. There's some additional finer instrumentation you can do on Android, especially wake locks, job schedulers, and alarms. Wake locks basically keep the CPU awake, so you shouldn't be holding them for long. So just instrumenting how long your app is holding wake locks helps, and also helps you detect if you forgot to release wake lock somewhere. Job schedulers and alarms basically are responsible for running your app in the background. So it's very easy to make a mistake where you wanted to schedule something at every 5 minutes and you ended up doing it every 30 seconds. And that will start draining battery really fast. So just instrumenting how frequently your app is waking up because of job schedulers and alarms helps basically monitor the battery drain. Finally, some key points to keep in mind for being a better battery citizen. Users don't like an app when it does stuff in the background, especially when the user is not using the app. Please don't do anything in the background unless you need it. Even if you absolutely need it, please don't do it. Be very careful of wake locks. As I said earlier, wake locks basically keep the CPU awake, and if you forget to release wake locks, the CPU will never go to sleep, and the phone will continue to use power for an entire night of sleep. In Android, there can be certain events which can be very frequent. For example, if your app is listening to something like network connected, disconnected events, these can be very frequent for certain users, especially in poor networks. It can be more than 200 times an hour. So just imagine your app reacting to each of these events in the background, which is probably not necessary. So make sure you're not listening to events that are not absolutely critical for you. Using job scheduler inexact alarms will help the OS batch the jobs across all the apps in the system together, and that helps the phone to sleep for a longer time and just wake up for a small window. CPU spins are real. An infinite loop in your code base can make the phone hot and drain battery really fast, so make sure you have the right tooling to detect and fix them. Animation leaks, as I talk about, we have found that not only in our app, but in many apps. So it's very easy to make these bugs. So make sure an easy way to test is to enable the GPU rendering profiler. The same things that the bar was moving from the left to the right. You can just use your app and see where the GPU is rendering the screen even without nothing changing on the screen. Camera is one of the most expensive components on the phone. Make sure you always close the camera after you use it. Fetching location at GPS is way more expensive than getting it via Wi-Fi scans. So if you only need a city level or a block level accuracy, you probably don't need to fetch locations via GPS.
Finally, we recently released a small open source project called Battery Metrics that helps in all the instrumentation we talked about earlier. It's like for capturing CPU, network, and camera and all of those things. We are actively using it in production at Facebook, and this kind of works across all Android versions, which is kind of important to us because we really want to know what our users are experiencing. And things like CPU time and network utilization, which we can capture from /proc, those just work, and there are some hooks that you can use for all the other custom instrumentation, and this will make life a bit easier for you if you use this library. The API is fairly simple. You just create a collector that says that I want to collect all of these metrics, and then at any interesting point, you can take a snapshot of that metric across your app. And then if you ever want to see, okay, how much work did I do in between these two periods, you can just subtract that, and that gives you that value And this just works across different types of information. And we've kind of found that mapping this data into this format has worked for any different kinds of use cases, like whether a product wants to instrument just its own instrumentation, or we wanted to measure background, foreground utilization of Facebook. That thing also just composes nicely. So if you wanted more than one type of collector, you just switch the CPU metrics collector with the composite metrics collector, and things still just work. All of this is available at Facebook Incubator /Battery Metrics. This is kind of an alpha release. We just open sourced it like 2 weeks ago, and we're really looking for feedback. And if you want to integrate it in your app, like, feel free to reach out to us, and we'll help you with any questions or problems you might have, and finalize the API. Like, we're just calling this an alpha release till we get some more users and feedback on the API, and then we'll firm it up and do a V1 after this. Thank you all for attending our talk, especially being the last talk of the conference. And if you have any questions.
How does something like React Native affect battery performance compared to like standard Java or Kotlin code?
I think we've noticed it's slightly more expensive, but it's not anything that comes up as a big drain in energy. It's like there is a slight extra cost of running JavaScript, and it makes debugging a bit more tricky because now you have a native thread that's running. But we haven't noticed, and we've also seen animation leaks through React, but you can have crappy JavaScript code and you can have crappy Java code. So, but nothing specifically stood out from just being React, just having a second, not more than you would expect.
Like a couple of percent?
Less than that, yeah. Anyone else?
Thank you.
Thank you.